Assalamualaikum everyone. I'm Hetisham Kader and I'm going to discuss the basic of DC transient analysis as applied to series RL, series RC and series RLC circuit. Before a circuit attains its steady state, the circuit passes through a transition period in which the current and voltage are not requiring periodic function of time. The period required for the currents and voltage to adjust themselves to their steady state is called the transient period. During transient period, the mathematical expression of the current and voltage contains two significant terms, transient and steady state. The transient terms are usually of short duration and damped out by certain damping factors, which depends upon the circuit parameters. Now, in general, when the switch is closed or open in a circuit or if any voltage source is suddenly induced, transient condition exists in the circuit. The simplest tension is one of that occurs when a constant voltage V is suddenly applied to a series RLC circuit in which no current flows at time equal to 0. By KVL, we can see that the voltage supplied is equal to the sum of voltage drop across the resistor and inductor. Expressing this voltage drop as a function of time, we know the voltage across the resistor is equal to the product of the current flowing through it multiplied by its resistance, while the voltage across the inductor is equivalent to the product of its inductance and the rate of current with respect to the time. The equation becomes VDC equal IR plus L di over. Rearranging this equation and writing it down as a standard form of a linear differential equation with the current as dependent variable, we can find the particular solution of the current. I of t equals VDC over R times the quantity 1 minus exponential negative R over L times t. This is the current response in a series RLC circuit in which the VDC over R is steady state component and VDC is over R exponential negative R over L times T is called a transient component. Now from this equation, as the value of time increases, the behavior of the current is generally represented by this graph. Now, another important parameter in tension analysis is what we call time constant. It is a measure of the rate at which the current builds up to its steady state value. That is when the current reaches to 63.2% of its steady state value and is given by the formula L over R. Example, a series RLC circuit is energized with 24 volts DC at time equal to 0. If R is equal to 10 ohms and L equals to 1 Henry, determine the following. For letter A, the current at any time t is given by the formula I of t equals V over R times 1 minus exponential negative R over LT. Now, substituting the values, we have 24 volts over 10 times 1 minus exponential negative 10 ohms over 1 Henry multiplied by time. Our final answer for letter A is equivalent to 2.4 quantity 1 minus exponential negative 10t. If you want to visualize this equation, it is more or less represented by this graph. Take note that while the current is increasing during the transient period, there will come a point in time where the current would fixed up to 2.4 ampere. Remember that the given circuit is a series connection of R and L whose supplies voltage is equal to 24 volts DC and whose R is equal to 10 ohm. If we treat the circuit as a purely resistive one and solve for current by dividing 24 over 10, the answer will be the same as that of steady state value. Therefore, it is really important to remember that for a series RLC circuit with a DC voltage source, as time approaches to infinity, the inductor will act as short circuit during the steady state period. For letter B, using the same current equation at t equal to 0.03 second, the value of current should be around 0.6 ampere. Letter C, the time it requires for the current to reach 100% is equivalent to 0.054 seconds. To calculate the voltage across R and L at any time t, the voltage across the resistor is given by the formula current times the resistance, with the current equal to 2.4 quantity 1 minus exponential negative 10t. Post resistance is equal to 10. The voltage across the resistor at any time t is equal to 24 quantity 1 minus exponential negative 10t volts. And last but not the least, to solve for the voltage across the inductor, the formula suggests we need to take the first derivative of the current with respect to time, whose result is 24 exponential negative 10t. After this, we finally go back to the formula and substitute the values. Thus, our final answer is 24 exponential negative 10t volts. Now we have series RC circuit. To able to find the current equation of a series RC circuit with a DC voltage source. By KVL, our equation is supply voltage V equals to the sum of the voltage drop across the resistor and a capacitor. Expressing the voltage drop as a function of time, we know that VR is equal to IR and the voltage across the capacitor is given by the formula 1 over C integral I dt. After we rewrite this equation, if we are going to differentiate the current I with respect to time, it will lead us to a more specific equation in the form of R di over dt plus I over C equivalent to 0. And from this linear differential equation of the first order, we find the particular solution of the current, which is equal to V over R exponential negative t over RC, whose initial condition is given by the voltage supplied V over the resistance R. Since at the particular moment the capacitor is acting as short circuit, this current equation, whose graphical representation is given by this, is applicable to any RC circuit with a capacitor having no initial charge. The time constant of a series RC circuit is the first where the capacitor is charged to 63.2% of its steady state value, and it is given by the formula R times C. For example, a series RC circuit is impressed with 12 volt DC if the resistance is equal to 10 ohm and the capacitance is equal to 0.001 farad. Assume no initial current at a conductor. Determine A. The current at any time t. B. Calculate the current at time equal to 0.5 seconds. C. Calculate the time when the current is equal to 0.75 ampere. Now for A, substitute the given value into our current equation so that we have 12 over 10 exponential negative t over 10 times 0.001. Our final answer will be equal to 1.2 exponential negative 100. Compare this equation. It approximately represented by this graph. Now with this, we can see that as time increases, the current behaves in a declining fashion. The reason for this is that if you have a series RC circuit with a DC voltage source, once the switch is closed, eventually the capacitor will open, and at the particular moment, the current has already decayed to 0. B. We want to calculate the value of the current at time equal to 0.5 second, and the answer is 2.31 times 10 to the negative 22. Practically speaking, this is already equivalent to 0. C. We want to calculate the time when current is equal to 0.75 ampere, and from the same equation we find the value of time equal to 4.7 milliseconds.